Hello all, welcome back. The statement reads, a point charge Q is nailed down on a table. Around it, at radius r, is a frictionless circular track on which a dipole P rides. Constrained always to point tangent to the circle. Show that the electric force on the dipole is F equal Q over 4 pi epsilon naught times P over r cubed. Notice that this force is always in the forward direction. You can easily confirm this by drawing a diagram showing the forces on the two ends of the dipole. Why isn't this a perpetual motion machine? For our solution, let's consider using cylindrical coordinates in the z equals 0 plane. So the dipole moment is this P in the phi hat direction. P dotted with the delta operator is P times 1 over S partial with respect to phi. And the electric field is just the electric field of a point charge, but in the S hat direction. So the force is equal to P dot del multiplied by E. And we see that there's a bunch of constants, so we just factor them out. And we're left with the partial derivative with respect to phi of S hat. If you recall, these S or the unit vectors in the spherical and cylindrical case are not one-to-one, so they are comprised and composed of sine and cosines of various arguments, and thus we're left with the phi hat for the derivative, and thus we simplify it down to Q over 4 pi epsilon naught r cubed times P, which is exactly what we started with. Qualitatively, the forces on the negative and positive ends, though equal in magnitude, point in slightly different directions, and they combine to make a net force in the forward direction. We can see this in the diagram. We have the z equals 0 plane, which is also known as the xy plane, and we see where P is and the force of the negative charge and the positive charge, and why it moves in a circular pattern. So why isn't this a perpetual motion machine? Well, to keep the dipole going in a circle, there must be a centripetal force exerted by the track. We may as well take it to act at the center of the dipole, and it is irrelevant to the problem. And to keep it aiming in the tangential direction, there must be a torque, which we could model by radial forces of equal magnitude acting at the two ends. Indeed, the dipole has the orientation indicated in the figure and is moving in the phi hat direction. The torque exerted by Q is clockwise, whereas the rotation is counterclockwise. So these constraint forces must actually be larger than the forces exerted by Q, and the net force will be in the backwards direction, tending to slow the dipole down. If the motion is in the negative phi hat direction, then the electric forces will dominate, and the net force will be in the direction of P. But this again will tend to slow it down.